So here we will define the transpose of a matrix. Sorry, I apologize for my handwriting. I will work on that. Of a matrix A, which is an element of M n by n of a field, is the matrix in which M n x n of a field, well, n by M, not n by n, sorry about that, such that A I J transpose equals A J I. So let's see an example of this just real quick. So if we have a matrix of 1, 4, 2, and 3, and this is the transpose, the original matrix, so A transpose equals, so now A will equal 1, 2, 4, 3. This equals A. So essentially what is happening is on this diagonal here, we are crossing it over. But it gets a little more complicated when we have different shaped matrices. Like this is a square matrices, so everything on the diagonal will stay the same. But let's say, for example, we have 1, -2, 3, 0, 5, -1. So the transpose of this matrix is going to be essentially the same process, like we flip it on the diagonal. So it will look like this. So A11 is going to equal that. And now we have, so since Aij equals Abi, we're flip-flopping. So now this position is going to be 0. And the next one below, we're going to go below 1 now, is going to be -2. And the one to the right of that is going to be 5. And so on and so forth. So you can see that we have a transpose of this. So this is the transpose, and so this equals A transpose, this equals A. So this is defining what a transpose is. Not really defining, but just an example of what it is, so then we can understand how to prove the subspace above. So to check if W is a subspace of matrix M, you have to do a few different steps. The first one is to check that the zero vector is there. So let's define what the zero vector is in terms of a matrix. So, that's the eraser. The zero matrix is the matrix 0, which equals, this is going to be kind of interesting, so 0, 0, 0, 0, put another 0 there, just, and these are just dots, 0, 0. So essentially, the zero matrix is the matrix where every position Aij equals 0. So Aij equals 0, no matter what. And that is the zero matrix. So if we have n equals 2, the matrix here would be 0, 0, 0, 0, because it's got degree 2. Now that we know what the zero matrix is, let's go ahead and check the first step. So the first thing to do is check that the zero vector exists. So zero vector equals 0, I, j. So that's defining that every position is 0. So A, I, j equals 0 equals A, j, I. So when you take the transpose of the zero matrix, let's say we have 0, 0, 0, 0, what is the transpose of that? Well, obviously that's just going to be 0, 0, 0, 0. So in fact, we do have that the zero vector exists. So for all I, j, we have that the zero vector is an element of W. So far, everything's working out. Now let's go to the next step. This is where we check. We are checking multiplication and addition. So we can do that in one step. We do if C is an element of fields, we just write F for that, comma, and A equals Aij, ij. So that's just a matrix of any size n, comma, and we have B equals Bij, ij, again, just a matrix of any size n, and both of these are an element of W, so that's important. Both of these matrices for the addition part have to be a matrix that are already an element of W. This is just to check if it's a subspace. This is one of the most important factors. They both have to be a part of W, because when you add them together, if you add a matrix that's obviously not a part of W, then it can't contribute to checking if it's a subspace. So here's what we'll do. So we can do this. We'll take the C here, because we have to check the multiplication of a scalar, and we can do CA plus B. And now we just check if this is true. So this equals CAIJ plus BIJIJ. So this so far is working out, and from this point on, we can say that it equals CAIJ plus BJIJ. So right here, we are putting in the transpose of B here. And this should equal the same thing because A comma B are symmetrical. Because of the definition up here where we had A transpose equals A. So that's part of the space here, the vector space. That's everything in the vector space has to abide by that rule. So Aij or Aji will equal the same exact thing. So in this case, well, actually, oops, I slipped up here. Sorry about that. This is also going to be Aji. Because of the fact we need to finish the proof here. So the last step here is we have this equals C times A plus B transpose. And this turns out to be true. So CA plus B is equal to CA plus B transpose. So therefore, we have CA plus B is an element of W. And because of this, W is a subspace of the matrix n by m.